Cycle 3, Lesson 18. We're continuing with trigonometry. Today we're going to look at something called compound angle formulas. And what that's about is combining what we know about special triangles and some properties of trigonometry to allow us to figure out exact values for other angles besides pi over 6, pi over 4, pi over 3. Because we already know the special triangles, and I've already sketched them here for pi over 4 on the left, and then a combination of pi over 3, pi over 6 on the right. Remember, pi over 4 is the equivalent of 45 degrees, pi over 3 is the equivalent of 60, and pi over 6 is the equivalent of 30 degrees. So we know how to use those. We also should know how to get the exact values of the angle 0, pi over 2, which is the equivalent of 90 degrees, pi, which is 180, and 2 pi, which equals 360. And if you've forgotten that, we'll take a look at that when I look at example 1, part B. But so let's start with what we already know. Find sine of pi over 3. It's quite simple with the special triangles. We're finding the exact value. Again, means put those calculators aside. We won't be using them. But for pi over 3, we find that angle, which is down here in this triangle. And then for sine, we do opposite over hypotenuse. Opposite is root 3, hypotenuse is 2, so it becomes simply root 3 over 2. And that's all there is to that one. It's that easy if you understand your special triangles. For cos pi, that one's not a special triangle, but we should understand that from the unit circle. Let me just draw a little Cartesian plane. And actually, I'm going to move it over a little bit. Let's move it over here a bit. So I'm going to draw a Cartesian plane. And for that, an angle of pi means start at the positive x-axis and go all the way around until you hit the negative x-axis, because pi is the equivalent of 180 degrees, right? So we've got this initial arm on the positive x-axis over here. I'm going to do that in red. And then we got the terminal arm, which is over here going the exact opposite direction. So it doesn't matter. Think of the unit circle. And on the unit circle, we would then have this point, -1, because it's on the negative x-axis, and 0 for the y value, because it's on the x-axis. So at this point, 0, 1. On the unit circle, we identified values as x, y, and r. So x is just our x-coordinate, which is -1. Y is just our y-coordinate, which is 0. And r is the radius. And the radius is just 1, because it's always positive. It can't be negative. And if this was a circle, then the radius of that circle would be the same as the x-coordinate. It would be 1. So those are our x, y, and r values. So we can use them to find the cos of pi must be equal to, as cos always is, adjacent over hypotenuse, or x over r, in terms of x, y, and r. So it would be -1 over 1, and so the cos of pi is just -1. And again, we can confirm this on our calculator. If you have your calculator set to radian mode and you type cos pi, it should equal -1. So we know how to do that as well. The next one, though, tan of pi over 12. Hopefully what becomes immediately obvious for this is that there is no special triangle that we know of for pi over 12. Which means that we can't obviously use something we don't have. What we can do, though, is we can break pi over 12 up, or rewrite pi over 12 in terms of the triangles we already know. So if I were to think of pi over 12, if I was to rewrite it as, say, either an addition or a subtraction, a sum or a difference between the triangles we already know, then I could then, of course, use them. So, for example, if I was to think of it as 4 pi over 12 minus 3 pi over 12. Then when I subtract, 4 pi minus 3 pi equals just pi over 12, same denominator, that would work out. But you may be wondering, why did I choose to make it 4 pi over 12 and 3 pi over 12? And that's because I was thinking in terms of equivalent fractions. 4 pi over 12 reduces to just pi over 3, which we have a special triangle for. Likewise, 3 pi over 12 reduces to pi over 4. We have a special triangle for that one as well. So I can take the tan of pi over 3 minus pi over 4, and then I would be able to figure out what the tan of pi over 12 is. However, we're not quite there yet. It's good to be able to break it down like this, but we need to have some formulas to work on it. So this is called a compound angle, by the way. It's made up of two parts, in other words. This whole thing together is our compound angle, and that's supposed to be the letter D. Compound, slightly better. All right, so how do I work this out? Well, what I do is I have these formulas. And so I have to now pick the correct formula, and then I can use that formula to finish off the question. So you can see that we've got sine, a couple of sine, we got a couple of coses, we got a couple of tans. Let's say I wanted to keep working on part C. Well, that's a tan, so I'd go to one of the tan ones, and then the other thing I have to decide is, notice how these are all plus addition formulas and these are all subtraction formulas. So I'd find the tan, so I'd find the trig ratio I want, and I also find whether it's adding or subtracting. So if I was going to keep going with part C, which I'm not at the moment, but if I was, I would pick this version of the formula here because it's tan and it's subtraction. So how do you remember the formulas? Well, here's some things that you can read through. Well, I'll read through them, but you can refer back to. Subtraction formulas, if you notice line by line, subtraction formulas are exactly the same as addition ones except with opposite signs. Whatever the signs were under the addition formula column, just take all the signs and reverse them, and you've got your subtraction formulas. As far as the sign formulas go, this top row, notice how it's a sine times cos plus cos times sine. So we're mixing the sine and the cos together, whether it's addition or subtraction. Whereas for the cosine ones, it's cos times cos minus sine times sine, so we can remember it that way. As far as the tan formulas go, then notice that the sign in the numerator matches the sign of the original angle, whereas the sign of the denominator is the opposite. So we have a plus in this one, we got a plus on the top. If we got a minus in the right-hand one, we got a minus on the top, and they sort of mix, and they're opposites once again. So these are just some ways to help remember these formulas. Anyway, let's put them to use. The first question is to rewrite to simplify each trigonometric expression. So if we go back to these formulas, and maybe I will get rid of all this highlighting, which is a bit distracting. What we want to do is we want to start with something that's all expanded out, cos times cos plus sine times sine, and rewrite it as something simpler. So cos times cos plus sine times sine, and I'm not even worrying what the angles are right now, that looks like this one here, right? Cos A times cos B plus sine A times sine B. I could work that backwards and write it as cos A minus B. So instead of having A and B, what I've got is 7 pi over 12 and 5 pi over 12. So those are my A and my B's as far as the formula goes. A, B, A, B. So to use the formula and go backwards, that one was, what was it equal to? Well, it was equal to cos A minus B. So I can now write it as cos. I know now that it's a cos, and A was 7 pi over 12. And I think it was minus. I said it was minus. I'm sure it is minus, but never hurts to double check. Yep, A minus B. So great. So we've rewritten it like that. So what? Well, 7 pi minus over 12 minus 5 pi over 12 can be simplified further. All I have to do is write it as 2 pi over 12, and that reduces even farther. That's cos of pi over 6. So this long formula was worked backwards to be made into something easier to work with. Doing the same thing for part B, sine cos minus cosine. What does that look like in the formula? Well, sine cos minus cosine looks like this subtraction formula here. So it's going to be equal to sine A minus B. But what are A and B again? This would be my A, and X would be my B. So it would be 2x minus x, which again we can simplify just down to sine of x. All right, so that's going backwards. So if you see a big long formula and you're asked to simplify it, you can go backwards. But to actually go forwards and do some calculations, that's going to be like what I started off with. So we've already seen that pi over 12 doesn't have a special triangle, but we have also already seen that I could rewrite pi over 12 as pi over 3 minus pi over 4. So let's do that. Okay, so that's the first step, is just breaking it up. And then we think of this as A and this is B, right? Again, think AB. And let's go to the formulas above again. Let's find the one that's cos and subtraction. So cos combined with subtraction is back to this one. So cos A times cos B plus sine A times sine B. Cos A, but A is pi over 3, times cos B, but B is pi over 4, and it was plus sine A, pi over 3 again, not cos, sine B, which is pi over 4. Now, I've already drawn the special triangles here for our reference again. What we have to do is we have to use the special triangles not once, not twice, but 4 times to help us work this out. So, let's do some highlighting again, because why not? If you've got highlighters, you should use them. So I've got 4 different calculations that I've highlighted in 4 different colors here. Let's take them one at a time. Cos of pi over 3 means go to the pi over 3 triangle and do the cosine of it. Well, cos would be 1 adjacent over hypotenuse, 1/2. And I'm going to multiply that, I mostly use brackets, times cos of pi over 4. Pi over 4 is in this triangle here. Cos again would be adjacent over hypotenuse. So adjacent over hypotenuse is 1 over root 2 plus sine of pi over 3. Pi over 3 is back over here, but sine now is opposite over hypotenuse, so it's root 3 over 2. And then pi over 4 again. And I'm doing sine, so it's 1 over root 2 again. So highlighting, you can see where these different numbers came from. You know that we're not allowed to have radical numbers on the denominator, so we will have to deal with that, but I'm going to deal with that at the end. So let's just simplify everything first, multiply it all together. So 1 times 1 is 1, and 2 times root 2 is root 2. And root 3 times 1 is root 3, and I get another 2 times root 2. So that's nice. So actually, since I've already got a common denominator, that works out quite well for me, because then I can just add the numerators 1 plus root 3 over 2 root 2. So everything's great except for that radical sign in the denominator. So this is still our problem. I'm not supposed to leave radical signs in the denominator, so the way I'm going to get around that, like I did before in the previous lesson, is I'm going to multiply by the smallest thing that'll get rid of that square root. So if I multiply by root 2, then multiplying the root 2 times the root 2 together, the square roots will cancel out. That'll just equal 2. But again, I can't multiply just the bottom by root 2. I have to do the same thing to the top. So when I do that, let's look at the bottom first. That root 2 times root 2 does equal 2. And then there's the other 2 out front. Well, do I want to? Yeah. So root 2 times root 2 is 2, but there's another 2 out front, so when I multiply that times 2, those together I get 4. So 2 times root 2 times another root 2 equals 4. Now as for the numerator, I've got a binomial here on the top times a monomial. So I've got to multiply each of the terms 1 and root 3 times root 2. When I do that, 1 times root 2 just equals root 2. And when I do root 3 times root 2, I get root 6. And there's nothing more I can do to simplify this one, so this would be my final answer. But those are the steps. So let's take a look at another one and think about how we could do this. So this time we start with the angle again. We always start with the angle, right? So 7 pi over 12. Don't have a special triangle for that, but how can we combine what we already know? We already saw that pi over 12 could be thought of as 4 pi over 12 minus 3 pi over 12. Then we reduced it, but it was 4 pi minus 3 pi to get pi in the numerator. What if I just added them together and did 4 pi over 12 plus 3 pi over 12? Then I'd get 7 pi over 12, right? So that's what we'll do. And in fact, I'll show it in unreduced form first. So 4 pi over 12 plus 3 pi over 12. But we know that reduces to pi over 3 and pi over 4. And we have special triangles for that. We also have a formula for that. So we're using 10 and we're using addition. When we do that, 10 combined with addition would be this one here, 10a plus 10b over 1 minus 10a times 10b. Once again, we have to be clear on what we're thinking of as a and b. So let's call pi over 3 our a value, call pi over 4 our b value, and so we then have 10 pi over 3 plus 10 pi over 4 all over 1 minus 10 pi over 3 times 10 pi over 4. So this formula looks a bit more awkward because it's got the fraction built into it, but we're going to do the exact same thing. So again, we've got these really, actually, in this case, we've only got two different things we have to do. We have to find out what tan pi over 3 is, because it turns up twice, and then tan pi over 4 also turns up twice. So going back to our special triangles, find pi over 3, and that's here. And if I want the tan of that, that's opposite over adjacent, so it's root 3 over 1, which is just root 3. So tan of pi over 3 is root 3. Tan of pi over 4 from this triangle here, opposite over adjacent is 1 over 1, so tan of pi over 4 is just 1. That's where that came from. On the denominator, I've got 1 minus root 3 times 1, because I'm just doing tan of pi over 3 again, which was root 3, and tan of pi over 4 again, which is just 1. So we've got this. If I simplify it a bit and stop highlighting things, I get root 3 plus 1 over 1 minus root 3, which is great, except once again, I've got this radical on the bottom. This one may look similar to what we just did, but it's a little different, because this is a 1 on the numerator, on the denominator, it's a 1 minus root 3. It's part of a binomial. And because it's part of a binomial, I can't just multiply by root 3 to get rid of the denominator, because if I multiply everything by root 3, I'd have to multiply the 1 by root 3 as well, and I'd still have a radical on the bottom. So what I can do is I can multiply by the opposite. So if I got 1 minus root 3, I can multiply by 1 plus root 3. Think of difference of squares where you have two factors that are the same, but the two middle terms cancel out. This kind of thing is going to happen if I multiply by the same binomial but with the opposite sign in the bottom. I have to do the same on the top though. So I'm going to multiply top and bottom by 1 plus root 3, and let's see what happens. Let's go a little higher up so I can have as much space as possible. All right, so I'm going to, let me just rewrite it actually. Root 3 plus 1 over 1 minus root 3 times 1 plus root 3 over 1 plus root 3. So I'm going to do FOIL on the top. So let's just look at the top. I'm going to multiply root 3 times 1 and root 3 times 3, and I'm going to multiply 1 times 1, and I'm going to multiply 1 times root 3. When I do that, and this is just for the numerator, I'm going to get root 3 plus 3, because root 3 times root 3 just equals 3. 1 times 1 is 1. And I'm going to get another root 3. No. Yes, sorry, no, I'm going to get, another root 3 there. Then, on the bottom, I'm going to do the same thing. So there, I'm going to multiply 1 times 1 and 1 times root 3. I'm going to multiply root 3 times 1, negative root 3 times 1, and negative root 3 times 3. And when I do that, I get 1 plus root 3 minus root 3, and then negative root 3 times positive root 3 just gives me 3. And that's what I've got on the bottom. That's where I see my difference of squares. So when I simplify, the two middle terms are going to cancel out. So again, let's just look at the bottom first, because that's where the action is. This plus root 3 and minus root 3 cancel out nicely, leaving me with just 4 on the bottom. On the top, I'm still going to have some radical signs, but that doesn't matter. But I can at least group them together. I've got 4. 3 plus 1 is 4. And I've got root 3 plus root 3. which is, I can write as 2 root 3s. And I can simplify a bit. I can't just cancel out the 4s. That is not allowed because I have to divide everything by 4. But what I can do is I can find a number that goes into both terms. So is there something that goes into both 4 and 2 and the 4 on the bottom? And yeah, I can divide everything in half. Maybe actually I'll show it this way. What if I were to common factor 2 out of the top? If I common factor 2 out of the top, I'm left with 2, and then times 2 plus root 3 over 4. Now that I've factored it and everything's multiplied, I can reduce this 2 with this 4, and I'm left with 2 plus root 3 over 2. And that's as far as it can be reduced.